Welcome to another fantastic factoring edition of Comet Algebra. This video is for Algebra 1, Chapter 10, Section 4, Factoring Special Patterns. So if we can learn to recognize some of these special patterns, the factoring can be so much easier and you can save yourself a ton of work that you don't have to use the diamond method for. So one of the things that is very helpful for you to do is to be able to recognize perfect squares. That's why pretty soon in class, you're going to be able to take a quiz and hopefully quickly fill this in. I'll give it to you like this, and you'll need to know 1 times 1 is 1, 1, 4, 9, 16, 25, 36, and so on. The reason I'm going to do that is because when you recognize these, it's so helpful in factoring. So let's think back a minute when you learned in the foiling in Chapter 9. And you were foiling something like x plus 3 and x minus 3. And something unusual happened with the foiling. When you did the outer and the inner product and looked at what you have, they subtracted to nothing. They were gone. And your answer was just x squared minus 9. Well, what we're going to do with factoring special patterns, we're going to start with this, and then we're going to factor it into its x plus 3 and x minus 3. So we write that the binomial here times another binomial with this binomial has a plus sign and this one has a minus sign. And when that happens, that's when they add it to 0. And they were special. And because they're special, they have a special name. They are called conjugates. Now we're going to do a ton of work with conjugates in Algebra 2, but for right here in Algebra 1, I want you to know the name and know what they are. So they're a binomial that only differ by a plus and a minus sign. So in the example here, if we're asked to name the conjugate of x plus 7, all we need to do is take out the plus sign and put in a minus sign. So the conjugate here would be x minus 7. The conjugate of y minus 4 is y plus 4. The conjugate of 4a minus 3b is 4a plus 3b. So we write this in general terms. Any a squared minus b squared, and notice this does have to be a subtract sign, can be factored into its two conjugates. So a quick example of that could be like x squared minus 25. If you recognize x squared as a perfect square and 25 as a perfect square, then you know that you could factor this into their square roots. Square root of x squared is x. Square root of 25 is 5. So we want to see if this factors into x plus 5, x minus 5. And then if you FOIL this, the inner product is a positive 5x. The outer product is a negative 5x. They do indeed add to 0. So you're just left with the x squared minus 25. And just to point out again, this does have to be a difference. This does have to be a subtract sign. If you were given x squared plus 25 to factor, we couldn't right now. It doesn't work to factor into x plus 5, x minus 5, or you couldn't even factor this into x plus 5, x plus 5, because that would give you a trinomial, x squared plus 10x plus 25. So please notice, if this is a plus sign, right now we can't factor it. It has to be the difference of two perfect squares. Let's do a few examples. A squared minus 16. Now when you get this on a factoring worksheet, you might think, oh no, I can't use the diamond method. I don't have a trinomial, and there is no middle term. And you're right. And then you may look for GCF and it doesn't have one. So I hope you recognize this a squared is a perfect square, and so is the 16. And so this is the conjugate factoring into a plus 4, a minus 4, and if you FOIL this, you will have the positive 4a and the negative 4a, which add to 0, and you will get this original binomial. Same thing with example 2. We recognize this as a perfect square. 9y squared is a perfect square, so we suspect this is a conjugate factoring problem. So we do their square roots. So we have 2x plus 3y and 2x minus 3y. And again, if you FOIL it, the outer and inner product add to 0, and we're left with the 4x squared minus the 3y. Minus the 9y. So this factoring checks out. And then we hit something like number 3, and we can't use the diamond because there's no b term, and 5 isn't a perfect square, so we think we're stuck, but I want you to always remember to look for a GCF. Your life will be so much easier if you keep that in mind. These numbers both share a 5, so we can GCF a 5 from both of these. 5 divided by 5 is 1. 125 divided by 5 is 25. And now we do, I hope, recognize this as the difference of two perfect squares. Don't forget, 1 is a perfect square. Because 1 times 1 is 1. Sometimes it's the easy ones we forget. And this, we suspect, is conjugate factoring into 1 plus 5b and 1 minus 5b. And please notice the GCF has to stay in your answer. Then if you FOIL these conjugates, you do get 1 minus 25b squared, and distributing the 5, we do get back to our original problem. All right, now why don't you push pause on the video and try number 4, and please keep in mind you may have to look for a GCF first. I hope you saw that they do share a GCF of 2, and factor that out first. And then 64 is a perfect square, so is x squared. So this is a conjugate problem. 2x plus 8, 2 is in front. X plus 8 is in the parentheses, and x minus 8. And if you FOIL that out and then distribute your 2, this factoring checks. Another special case we need to learn how to factor are called perfect square trinomials. So I'd like you to remember when you learned how to FOIL something like a plus 3, that FOILed into a squared plus 3a, which was a plus 6a, plus 9. So we're going to write that in general terms. A plus b times a plus b is a squared plus 2ab, because there was a 3a and a 3a. There was 2 of them. And likewise, the same thing it'd be similar if I had a minus 3 times a minus 3. I'd get a squared minus 6a, but still plus 9. So these are called perfect trinomial squares because the first term is a perfect square, the last term is a perfect square, and the middle term is the outer plus the inner product. And this can be really handy to recognize, and it can save you a lot of work. If you recognize them, then you won't have to do the diamond. So, of course, we're going to be doing these backwards. We're going to be starting with this trinomial and factoring it into its 2 binomials. In general terms, then, when you have a squared plus 2ab plus b squared, that factors into a plus b times a plus b. But we don't have to write it that way. We could shorten it a bit and write it as a plus b squared. I would accept either of these answers perfectly fine. And of course, if that middle term is negative, a squared minus 2ab plus b squared would be the 2 binomials a minus b, and of course we can write that as a minus b quantity squared. So let's look at a few of these examples. So if you're cruising along on a factoring worksheet and you come to a problem like number 1, you could certainly do this with the diamond method and it'd be no problem. But if you recognize that this is a perfect square and this is a perfect square, all you would need to do is check this middle term, because you suspect it could be the square root of a squared is a, the square root of 25 is 5, and this middle term is positive. So right now you have a suspicion that it might be a plus 5. So you need to check this middle term. The inner product is 5a and the outer product is 5a, and they do indeed add to a 10a. So this factoring checks out and you didn't need to do the diamond. Likewise, here in number 2, we suspect this is a perfect trinomial square because this is a perfect square and so is 9y squared. So we need to check and make sure this middle term is correct. So we suspect this could be, and notice the minus sign here, this could be x minus 3y times x minus 3y. And so we check our inner product is negative 3xy, our outer product is negative 3xy, and that does indeed add up to a negative 6xy. So you could write the answer like this, or remember you could shorten it and write it as x minus 3y quantity squared, whatever you prefer. So now we come across a problem like number 3, and this kind of looks like a mess because we don't have any perfect squares. But again, we always have to remember to look for a GCF first. And if we notice these are all even, they clearly have a GCF of 2. So let's factor out a 2 and then see what we have. And now you could go ahead and do the regular diamond on what you have in parentheses. Or if you observed that x squared is a perfect square and so is 49, you may have the perfect trinomial square that factors into x, and notice this is a negative sign, x minus 7, x minus 7. Check your inner term to inner product is negative 7x, outer product is negative 7x. That does indeed add up to a negative 14x. So this checks out. Please keep the 2 as part of your answer. And if you want to combine your binomials, you could write this as 2 times x minus 7 quantity squared. And that'd be perfectly fine. Either one of these would be okay with me. So now number 4. Oh, what a mess. Our life would be easier if 3 was a GCF. So let's do some dividing and check. And they all do divide by 3. So we have an x squared. 24 divided by 3, 72 divided by 3 is 24. And if I did this right, 432 divided by 3 is 144. So I have a 144y squared. And because we know the perfect squares, we suspect that this could be a perfect trinomial square. So let's check. Is it x minus 12y times x minus 12y? Remember, we just take the square root of the first one and the square root of the last one and check to see if we get this middle term. The inner product is negative 12xy. The outer product is negative 12xy, and that does indeed add to a negative 24xy. So you could leave your answer like this, or you could combine it and write it as x minus 12y quantity squared, but please remember to keep your 3 in front. All right, now you have the knowledge you need to factor these special patterns. I hope you see them in your factoring, and it does make it a little easier for you. So have fun with math.